Hello students, let us go ahead with quantum physics. In this lecture, we will talk about energy of matter waves and concept of a wave group. We know that the particle of mass m, when it is moving with velocity v, particle of mass m moving with a velocity v, it has a wave associated with it which is called as a matter wave. The wavelength of which by this de Broglie hypothesis is given by lambda equal to h upon p is equal to h upon mv, where mv is the momentum of the particle. So, for a quantum particle, the movement is governed by this de Broglie hypothesis. Every moving particle has a wave associated with it. So, and the wavelength of which is lambda equal to h upon p. Let us derive an expression for wavelength of matter waves in terms of energy E of the particle. So, de Broglie hypothesis is given by lambda equal to h upon mv is equal to h upon p. Now, energy E of the particle is given by half mv square. So, it is a freely moving particle. It is a freely moving particle, so its energy is kinetic energy. It is half mv square. So, this can be written as 1 by 2m m square v square. Why? Because we can write it in terms of p. So, E is equal to p square by 2m. So, this p will be equal to under root twice m e. So we can simply have an expression for lambda is equal to h upon p is equal to h upon under root twice m e. So this is lambda, wavelength of matter waves in terms of energy E of the particle. Further, if it is a charged particle, if this moving particle is a charged particle which has been accelerated through a potential difference of V volts. Let it is a charged particle accelerated through a potential difference of V volts, then this energy E will be Q into V, where Q is a charge, V is a potential difference. So in this case, this lambda, so for a charged particle which has been accelerated through a potential difference of V volts, lambda will be equal to h upon under root twice m q into V. So this will be an expression for lambda for a charged particle with charge q accelerated through a potential difference of V volts. So now we know that the wavelength of matter waves for a charged particle is lambda equal to h upon under root twice m q into V. So if we want to have the wavelength of matter waves for an electron, so Q will be equal to E 1.6 into 10 raised to minus 19 coulomb. V is volts, potential difference applied. M is mass of an electron. It is 9.1 into 10 raised to minus 31 kilograms. H is a Planck's constant, 6.63 into 10 raised to minus 34 joule second. So these values, putting these values in this above formula we can have an expression, we can have calculate the wavelength of matter waves. 6.63 into 10 raised to minus 34 divided by, we will just put these values. Keeping V as it is. So we will just calculate this. This will be 31, 9, 40, 50. So this will be 25 because it is square root. All quantities we have taken in SI units. So this will give us in meter. So this lambda comes out to be equal to, so this gives lambda is equal to 12.27 divided by square root of V into 10 raised to minus 10 meters. Hence lambda is equal to 12.27 divided by root V angstrom units. So herein we have calculated the wavelength of matter waves. If an electron has been accelerated through V volts, then de Broglie says that electron is not a particle, it has a wave associated with it, and this wave is called as matter wave. So using the formula which we derived, so we are calculating here the wavelength of matter waves for these electrons. It comes out to be 12.27 divided by root V angstrom units. So this gives us an idea about the wavelength of matter waves for an electron. So if this voltage is 100 volts, so what will be the wavelength of matter waves? So this lambda will be equal to 1.227 angstrom units, right? So this formula helps us to calculate the wavelength of matter waves. Such a numerical can be there in the examination. So if it is for an electron, if the numerical is for an electron, we can directly start with this formula. For the other particles like proton, neutron, we should start with this formula. So let us talk about the wavelength of matter waves again, but now by analogy with radiation. What is analogy? Analogy is similarity. So for the radiation has dual nature, we know that. By Planck's quantum theory, this E is equal to h mu. It is the nature of photons, no? It is the nature of light that it travels in the form of beam of particle which are called as photons. So this mu is the frequency of photons. E is equal to h mu. H is Planck's constant. Whereas Einstein's mass energy relation always gives us that E is equal to mc square. This is Einstein's mass energy relation. So if we are applying both these to a photon, then we should be able to equate these two. The photon with a frequency mu should be equal to or should be equivalent to a particle of mass m, mc square, right? So what is this? This we are deriving it for a photon. These are the things related to photon only, right? So this mu is equal to hc upon lambda. So we can write hc upon lambda is equal to mc square as mu is equal to c upon lambda. So here what we want wavelength of radiation. We want a wavelength of radiation. So lambda will be equal to hc upon mc. Lambda will be equal to hc upon mc square will be equal to h upon mc. So see, what is this? This we have derived the wavelength of waves for a photon. For a photon, wavelength of waves for a photon. This is for radiation. Everything is about radiation. So this wavelength comes out to be equal to h upon mc. C is the velocity of the photon. So this, now we want to apply this analogy to a matter particle. So for a matter particle of mass m moving with velocity v, this wavelength of matter waves will be given by h upon mv. Here photon was traveling with a velocity c. Now the matter particle cannot travel with velocity c, its velocity is v. So we want here to treat photon and a matter particle equally, right? So the wavelength of matter waves comes out to be equal to h upon mv. Now let us talk about velocity of matter waves. The velocity of a wave. Velocity of a wave is given by mu into lambda, where mu is the frequency, lambda is wavelength. It is frequency into wavelength. So what is frequency mu of a wave? We know that mc square is equal to h mu. If we are equating this Einstein's mass energy relation and Planck's quantum theory of radiation, by Einstein's mass energy relation, E is equal to mc square, and by Planck's quantum theory of radiation, E is equal to h mu. So this mu will be equal to mc square upon h, right? This is for radiation, but now the same thing we will apply for a matter wave, because we want to apply the same. We are using analogy. Whatever we are applying to radiation, with the same thing we are applying to a matter. Matter and radiation are equivalent, right? So the photon of mu, frequency mu, will be equivalent to a mass of a particle of a mass m. So mc square is equal to h mu, which will give us mu is equal to, in that case, the frequency mu of a photon will be given by mc square upon h. Now the same thing we will apply to a matter particle of mass m also. Now this is the same thing we are applying to a matter particle of mass m. And by de Broglie hypothesis for of a matter waves, this lambda is equal to h upon mv. Lambda is equal to h upon mv. So now both of these we will put it here. So then we will get the wave velocity of matter waves u is equal to mc square upon h into h upon mv. So it will come out to be c square by v. So the wave velocity of matter waves, it comes out to be c square upon v. What is the c? Is the velocity of light. What is v? Is the velocity of particle with which the particle is moving. Obviously, what will be our first comment when we see this formula? Our first comment will be equal to u, the wave velocity of matter waves, is much greater than velocity of light, because the velocity of particle is always less than c. So this u, the wave velocity of matter waves, comes out to be greater than velocity of light. This result makes it difficult to accept this wave nature of matter. because we know that nothing can travel faster than light. Nothing can travel faster than light. So this becomes a difficulty to this de Broglie hypothesis, how we can attach this wave nature to a matter. If we are attaching a wave nature, then the wave velocity comes greater than velocity of light, which cannot be true. So what is the what we can say here, we have to apply some other type of wave which is not a sine wave or cosine wave, monochromatic wave. If we are applying this monochromatic wave, such a wave, right, u is equal to mu into lambda, then we get a result which cannot be true. So we have to think of some different kind of waves. These are not like a simple sine wave or a cosine wave which is spread over a large region of space, which is spread over a large region of space. Such a wave cannot be attached to a matter particle. We have to think of different type of waves. See, students, this is what we have seen. See, now let us try to see what is this concept of a wave group. We said that when we attach a simple single sine wave or cosine wave, this wave velocity comes out to be c square by v, which is much greater than c, and hence we said that some new type of wave is required to represent these matter waves. So what is this new kind of wave? It is a wave group, or it is a wave packet. What is this wave group or a wave packet? So first, it is interference of infinite number of waves. Infinite number of waves. How are these waves? Infinite number of waves of slightly different amplitudes. And slightly different frequencies. It is interference of infinite number of waves of a slightly different amplitudes, of slightly different frequencies, such that the resultant wave produces a hump in the vicinity of the particle. And diminishes away from the particle. So it is interference of infinite number of waves of slightly different amplitudes, slightly different frequencies, such that the resultant wave produces a hump. Hump is a rise, sudden rise. In the vicinity near the particle, it produces a hump, and away from the particle, this disturbance goes on decreasing. Let us try to understand. Let us try to understand the so, roughly, let us try to draw a diagram. So, let us consider the interference of few number of waves. So, this is the interference of few number of waves. How will be this interference? Again, it will be like this, right? It will be like this. So, this is interference of large, say few number of waves. What is this? Is called as a weak disturbance. weak disturbance. So there where this is a region between the two wave groups. So these are the two wave groups and this is a region of weak disturbance. It is this, the region of weak disturbance between two wave packets. When the number of waves interfering, it goes on increasing. Here say 6 to 7 waves we have shown. So here if this interfering waves go on, it goes on increasing, this weak region becomes wider and wider. The separation between these two wave groups, the separation between the wave groups will be wider and wider, wider and wider. And finally, when this number of waves becomes infinite, then this resultant wave is a single hump. The resultant is a single hump. When this number of waves becomes infinite, the number of waves becomes increasing, this wider, this region, separation between the two wave groups will be wider and wider. And when this finally in the limit, when this number of waves becomes infinite, then it becomes a single hump like this. So this will be the resultant wave then, like this. So it will result in a single hump. There is no disturbance outside. So this will be called as a wave packet. This will be called as a wave packet. See, this is a interference of waves, whereas this is a region of weaker disturbance. So when this number of waves goes on increasing, then this two wave groups, they will be more and more separate. And finally, when this number of waves it becomes infinite, interfering waves becomes infinite, then it results in a single hump. So this will be the wave packet. There is no disturbance outside, right? So this is a concept. Such are the waves which are associated with a moving particle, with a moving quantum particle, right? So there it is not a single sine wave or cosine wave, but it is a wave group which is associated with a wave packet, with a moving particle. Look at this, students. This is what we have seen. See, this is a wave packet, right? So, what is the velocity with this wave group moves, right? So now we know that phase velocity. What is a phase velocity, or which is also called as wave velocity, phase velocity or wave velocity. So what is it? We know that a single wave, it is a velocity with which a particular phase of the wave moves. It is a velocity with which a particular phase of the wave moves. It is equal to omega upon k, or it is equal to what, mu into lambda. Mu is a frequency, lambda is the wavelength. This is called as a wave velocity, right? So the typical wave has a formula, has an expression like this: sine of omega t minus kx. So the phase velocity of this wave, or wave velocity of such a wave, is given by omega upon k, or mu into lambda. This is called as a phase velocity. But now we know that it is not this single kind of wave which is associated with a moving matter. It is a wave group. right? And the velocity with which this wave group moves, the velocity with which this wave group is moving, it is called as group velocity. It is called as group velocity. So, group velocity. It is the velocity with which this wave group moves. Here, we can write this as Vp for phase velocity. Vp for phase velocity is omega upon k. It is mu into lambda, whereas Vg is the group velocity with which this wave group moves. It is equal to d omega upon dk. D omega upon dk. The rate at which this omega angular frequencies of the wave moves, d omega divided by dk with respect to the propagation constant. This d omega upon dk gives us the group velocity. By a simple derivation, it can be shown that this d omega upon dk comes out to be the particle velocity v. It comes out to be the particle velocity v only. It is particle velocity. So then it becomes acceptable result. The velocity with which this wave group moves, it is equal to particle velocity v. So now it becomes acceptable, right? Because when we were attaching such a single wave, it was we arrived at a result that u is c square by v, or the velocity of a wave is c square by upon v, whereas if we attach a group of waves to a moving particle, then this group velocity comes out to be velocity of the particle only. So now it becomes an acceptable result. Look at this, students. This is what we have seen. The definition of phase velocity and group velocity. This uh, this U can be written as Vp as a phase velocity. U is a wave velocity, that is also called as phase velocity. I am only changing the notation here. Vp is phase velocity and Vg is group velocity. Only I am changing the notation. U is replaced by Vp. Only the notation is changed and nothing else. Vp is U, phase velocity or wave velocity. Thank you, students.